Lecture 5.6, Fundamentals of Series and Parallel Circuits. The fundamentals of series and parallel are independent of the type of element. That means it applies to capacitors, resistors, and inductors all the same. They each follow this process here. So the first thing that we got to do here is identify when elements are in series or parallel. So what we want to do is that we'll look at a series combination. And so when I look at a series combination, I imagine that I have a wire and then I have two elements connected like this. And what you're finding here is that in this situation, let's say that this right here, I'm going to call this element 1. This right here, I'm going to call element 2. Now remember, element 1 and 2 can be a capacitor, resistor, and inductor. It doesn't matter. So when I say I have a series combination, this is the focus right here. This single wire. And what you see here is that you have one connection between two elements. So then if I look at parallel combinations, then what we find here is that I still have two elements, but the difference this time is that there is one connection that connects the top of it and another connection that connects the bottom. So when I'm looking at these guys, you're seeing the following thing. I had my elements 1 and 2, but now you can see that there are two wires connecting both elements. So in this situation, we have two connections between two elements. And believe it or not, even though it does not look this way, they're actually almost the inverse property of each other here. Now, when I have this combination, we then say that the elements are then connected to a power supply. I prefer the word power supply, but it's okay to say battery, and some people say voltage source or whatever it is, but the bottom line is this: a power supply supplies both voltage and current. And that has a very specific meaning that we won't get into it in this chapter, but the next. So then I have some important points that we should go through. The first one is wires. Wires in circuits form equipotentials. And what that means here is that this is a single potential, which is meaningless. So what we say here is that this is not a voltage because there's no height change. Okay, there's no height change. So this is not a voltage, which then it tells us here is that it's just a potential value. 2. Power supplies are the source of the potential landscape. That tell charges how to move. And when we're talking about this, we really mean how current is moving in a circuit. So what we find here is that what this tells us here is that the power supply only job is to maintain a constant potential incline for charges to slide down the incline as well as supply current. So then the third thing that we should say here is that voltage, and we typically don't say voltage. A lot of the times we say voltage drops only occur across elements. So remember, when we say voltage, we mean a height change. Okay, so note that I differentiated between wires, which are equipotentials, they have no voltage. And then we talked about voltage, which is a height change. So now let's talk about series circuit fundamentals. So here we are. Series circuit fundamentals. So for the sake of argument, I'm going to put numbers into this circuit. So suppose I have a series circuit. So if I have a series circuit, I imagine that I have my power supply. And I'm going to give this power supply a value of 10 volts. So what that means here is that when I look at my circuit, I am seeing that I have one element here. I have a second element there. And then this guy comes all the way back to the battery. So according to what we've been using with color codes, I'm going to call this element 1 and this element 2. So what do I mean by this? Well, the bottom here is what we call the ground, which means 0 volts. And so that tells me that here at the bottom of the battery is the low, the top of the battery forms a high. So now we can draw an effective potential picture here. So I see, I'm pretty sure I'm going to run out of space. So I want to move this all the way down. And let's start right here like this. And I'm just going to try to save space just in case I run into it. So here I go. We have an effective potential picture. And what we said, we imagined that this guy is going to provide a landscape for this to happen. So then I have my voltage source right here. And what it does here is it comes up and then it creates an incline. So as I look at an incline, I am seeing this guy coming all the way down to the bottom here of the bottom of the incline like this. So once again, this guy represents my ground, and then this is my source. So then I can come in and then put all the little details that we've been doing before. So this is my power supply. And what this means here is that this whole line here, this whole line is an equipotential surface right there. That whole line. This is what we call the high. That whole red line is the high. So now this is element 1 and this is element 2. So when I'm looking at this, I need to identify my middle point, and it's this guy right here. You know what? I think I might use a different color just because I need for it to stand out. So I'm going to use purple. So purple tells me about the one connection for series. So now what happens? The potential sets up an incline that looks like this. So I have an incline, and this height, according to what we stated, that's a height of 10 volts from here to here. So what that means is that when I look at the current flowing in the circuit, you could see that the current is going to be coming out of the battery. And I want to be very careful how I say that. It then goes through 1, it comes out of 1, it goes through 2, and it's coming all the way around, and it comes all the way back to the battery. So in this situation, I'm going to call this current 1 because that's what's going to enter 1. And then this guy is going to be current 2 because that's going to enter this. And then if I follow the current all the way around, I'm going to say that this current is the current of the battery. And so that tells me that that's what's going to enter the bottom of the battery here. So this guy we then say that this here, this is the height set by the battery. That's what's responsible for it. So when I look at this path here, note that there's only a single loop. So the current only has one possible loop, one possible path, I should say. So that tells me that then the battery and the current through element 1 and 2 must be the same. Where else is the current going to go? You can't destroy current, so it has to be this way. And even though I didn't say this, I assume that you understand that that's my low right there. So this is telling me about the current. Now, what I'd like to do is that I'd like to copy this, and then I want to insert it right in here again. Because now I want to answer a different question. So now look what I'm doing. I'm going to get rid of all of the currents here. Okay. I don't care about the currents anymore because we have that in the other picture. So I'm going to move this slow and I'm going to bring it over here because that's an important picture. So now what is happening? What you're seeing here is that the total height is 10 volts. So if it's 10 volts, that means here that there's going to be a voltage across 1 and 2 because they have height changes. In other words, if I was to draw a line like here, this guy is going to tell me about the voltage of 1. That's the height of the voltage of 1. When I look at this other one here, this is going to tell me about the height of voltage 2. So when I'm looking at this thing, and here's where I'm really going to run out of space. So I got to be careful how I draw this. In fact, I'm going to combine this to try to make it as tight as possible. And so I will come back and manipulate this thing to make it a little bit cleaner. But here's what we know. We have a voltage. So what we see here is that the battery's voltage is being divided between elements 1 and 2. So in other words, I could say here that the total height has to be a combination of these heights right here. So again, if I color code these, all I'm saying is that that green height plus this blue height has to be the total height here. So in one scenario here, you could imagine that I have a situation that says, okay, my height is 10 volts. Maybe I have a combination of 4 plus 6 volts. And it all depends on the value of the element. So that's what it means for the current to be in a series circuit and the voltage. Currents only have one possible path, so they always have the same current. If I have a series circuit, the voltage has to be divided among the elements. So let's summarize this. So now I have series circuit characteristics. The first one here is that voltages are always divided among series elements. And this is how we write the voltage source is then the combination of the heights. This is known as Kirchhoff's voltage law. And we will talk about this in the next chapter. Now, the other thing that we have is it says this, that there is only one path for current to take. In other words, series elements always have the same current. In other words, it's really that the current of the battery is going to be the same as the current of one, which is the same as the current of two. This is another very important circuit theorem, which is known as Kirchhoff's current law. So now I have all these elements now, or series. Now let's go to parallel. Let's look at parallel fundamentals. So if I look at parallel fundamentals, then we have the following thing. So we have parallel circuit fundamentals. So most people, if they're going to have trouble with either series or parallel, it's going to be with parallel. So parallel circuits can take on different looks. As an example here, we've already said that imagine that I have one that looks like this. And the first one that we drew, I believe, I think we said that it was probably somewhere along the lines like this. So I can have a combination that looks like this. And this is exactly the same as this guy. Which is exactly the same as this one. And we can always make them more challenging. But a lot of the times, these are the possible combinations that you see. So if this is my power supply, and then you can see here is that I could now change these guys like this. So in other words, if I look at this here, this also has the combination of this, and these guys are all identical. The bottom line is that we need two connections. What are the two connections here? So if I look at my two connections, I'm going to say that this is one connection, This is the identical connection. This is the identical connection. So if I come in and I place another connection, I could say that now this is my second connection. And all of these in red and gray are the exact same combinations. Now, if I was to do this properly, I would be putting in my ground wherever the battery is at. Those are all identical. So now let's get into the details. So as we already showed, parallel elements have two connections. And in this situation, you're seeing the red and the gray wires. So that means here that, so parallel elements have two connections, implying these elements have only two equipotentials connecting them. So what we're saying here, so if I look at just one of these, okay? So let's just look at just one of these guys here. So what does that mean? So if I have a circuit, then that means that the red wire is connected here, the gray wire is connected here. So I know that the gray wire is 0, and that represents, in this situation, it represents the low. But in our situation, up here, it represents the high. So if we set our high to be 10 volts and everything is down to 0 volts, this immediately tells us then that the voltages of 1, 2, and the power supply all have the same voltage. This is an equipotential equal to 10 volts. This is an equipotential equal to 0 volts. That tells us here is that all elements have voltage of 10 minus 0, which is 10 volts. In other words, voltages are not divided in parallel circuits, which then tells us what we've already just said here is that the source voltage must be the same as the voltage of 1, must be the same as voltage of 2. However, the current shows different behavior. And what we want to do here is that we want to draw this a different way. So we picked one here. Now let's pick this guy right here. Okay, I want to look at this guy. So when I copy this guy and bring it down, I want to look at this circuit in detail here. Oh, I messed up here. So what we want to do is that we want to follow the current. So if we finish drawing the equipotential surfaces, we see that we have our red like this, and then our gray is down here at the bottom. So when I'm looking at this, what direction is the current coming? So what I'm going to say here is that the current is coming from the battery. And what it does here is it comes all the way to right here. And at this location right here, notice that there is a junction right there. So what I'm saying is that right here, there is a junction. And the most common way that people talk about it in circuits, they call this a node. So when it does this, this is what happens. The current splits. Part of the current is then going to go towards 1, which we call I1, and part of the current is going to go towards element 2. And then the important thing here is that then these guys are going to reconnect down here at the bottom. And what you're seeing here is that there's another node or junction. And then as a consequence, they add up again, and it's still the current of the battery. So what we're seeing here is that current is divided among its parallel elements. And then that just tells us that the current of the battery is then going to be the current through element 1 and the current through element 2. Again, color coding these to remind you that it really is 2 different currents as we're seeing right here. So now I could come in and I could say, what are the parallel circuit? So the parallel circuit characteristics. So it says this. It says 1. It says voltages are the same for all parallel elements. In other words, the voltage of the battery or the source voltage is also equal to the voltage across 1, which is the voltage across 2. And then 2 here, currents are always divided among parallel elements. In other words, so if I look at the total current, which is the current coming out of the battery, that is being divided by each of these elements.